Hello students, welcome to lecture number 16 of Computer Architecture course. Today's topic is associative cache memory. In the previous lecture, we've learned about the direct mapped caches. We've seen how the mapping process works from the RAM address to a cache. We've also seen the significance of tag bits and what is tag bit useful for. We've also learned about the formula through which the tag bits can be calculated. We've also learned about multi-word direct mapped cache memory and single word direct mapped cache memory. We've also learned about intensity fast math processor, and we've done few examples on direct mapped caches. Okay, and today what we're going to do is look at the other class, or rather the other classes of cache memory, that is called associative caches. Now associative caches can be of multiple types. It could be M-way associative cache or it could be fully associative cache. Okay, so we'll look at the structures today and do some examples, and I'll also give you the generic formula for you to understand how the mapping process works. Okay, so let's get started. So, introduction to associative cache. There are three cache schemes. The first is direct mapped cache, second is fully associative cache, and the third one is set associative cache. What happens in a fully associative cache is as follows. You have a block of main memory that can be placed in any location in the cache. Okay, so there is no mapping algorithm as such as you see in case of direct mapped caches. So in order to find a given block in fully associative cache, all the entries in the cache must be searched in parallel, because the block can be placed in any one of the locations. Okay, so therefore, as you could make out, that this is much faster scheme than the direct map caches. Now, since in order to make it faster and more practical, it is done in parallel with a comparator, because you would like to compare the tag bits from the RAM and the tag bits of the cache associated with each entry of the cache. Okay. Now, since it is faster and it is more practical to have it done using parallel comparators, so of course there is a trade-off involved in this. So the flip side is that increases the hardware cost effectively, making it only pragmatic for caches which are not having a large number of blocks. Okay. So since you are having a large number of comparators working in parallel to compare the tag bits, so therefore there is a flip side, which is that the hardware cost becomes very expensive, and therefore in order to have a pragmatic solution, we can only have fully associative caches or caches with a small number of blocks, not with a large number of blocks, because in case if you have that, then the number of comparators will be extremely large. Okay. Now, since you understand the basics of fully associative cache, now let us have a look at the set associative cache. So it is a middle range of cache designs lying between the direct map caches and fully associative caches. That is, it is neither at the extreme in case of direct map caches, or nor at the extreme of fully associative caches. It is just lying in somewhat in the middle. So why it is so is because in a set associative cache there is a fixed number of locations where each block can be placed. Okay, so in case of fully associative, the block can be placed in any location. In case of direct map, there is a specific algorithm through which the mapping of the RAM to the cache can happen. In this case, it is neither a specific location nor any location. It is just in between a particular place, that is a fixed number of locations within which the block can be placed. So a set associative cache with n locations for a block is called an n-way set associative cache. Okay, that is, there are n possible locations where the block can be placed. That's why it's called n-way set associative caches. Now this n-way set associative cache is also known as the degree of associativity. Okay. So, for example, 4-way set associative caches will have, will be called like 4-way set associative. Okay, 4-way set associative will be means that the associativity is equals to 4. that actually indicates that there will be 4 elements per set. Okay, I'll come to that gradually as we progress along the course. N-way set associative cache consists of a number of sets, each of which consists of n blocks, and each block in the memory maps to a unique set in the cache given by the index field. Okay, so each block in the memory maps to a unique set in the cache given by the value in the index field, and the block can be placed in any element of that particular set. So that's how it is different from the fully associative caches, where you can place in any location, and in case of direct map caches it goes to only a particular location specified by the index field. So therefore this combines the features of both the direct map cache and the fully associative cache. Therefore we call it that it's lying in the middle range of both the two different extreme classes of the cache mapping. Okay, now let's look at it using a formula. So the mapping of caches for direct map caches works as follows: that each block has only one place where it can appear in the cache, block address, modulo, number of blocks in the cache. So that's a particular place given by the cache index entry where the block of the RAM can actually be placed. In fully associative caches, the block can be placed anywhere in the cache, as I've said before, and in case of set associative caches, the block can be placed in any element of a specific set into the cache. So in any element of a specific set means we have to determine the set where it can be mapped. So the set is a group of blocks. It contains a number of blocks, that is a number of elements where the RAM information or block of RAM can actually be placed. So it is given by block address modulo the number of sets in the cache. Okay, how many sets of caches how many sets do you have in the cache? Basically, that's how it's mapped by. So since the block may be placed in any element of the cache, therefore all the tags of all the elements of the set must be searched in parallel. Okay. In case of fully associative cache, if you recall, we were actually searching all the elements together, right, in parallel using a comparator. Here we don't need to search all the elements using a comparator. Here we are only searching the elements within that particular set. Okay, so we are therefore searching, as in like we are comparing with the help of comparator all the tags of all the elements of the set. Okay, that is being searched and compared in order to find out if it matches. So if it matches, so it's a hit. If it doesn't match, then it will be placed in that particular location. Okay, now let's have a pictorial representation of what I said. So for example, if you have a 8 block cache and it is configured in all the 3 modes which I have spoken of. The first mode is a 2-way set associative cache, the second is a direct map cache, the third is a 4-way set associative cache, and the last one is fully associative cache. So it's basically in 4 modes, 3 modes in terms of associativity and 1 mode in terms of direct mapping. Okay, in total we have 4 modes and 3 modes for associativity. So in case of direct map caches, it's very obvious that you have a block ranging from 0 to 7. So this actually indicates that there are 8 blocks. So 0 to 7 is here, and then you have a tag bit and you have a data bit, and the same pattern is repeated for each of the block entries in the cache. Okay, so this is nothing but the cache index that we are basically referring to in case of direct map caches. In case of 2-way set associative caches, we basically would have 2 elements per set and we would have 4 sets. Okay, so therefore we have, as you would see, 2 elements per set. So it's tag data, 2 elements. Again, next one tag data in set number 1. Then you have set number 2, set number 3. So there are 4 sets, and each set has 2 elements. 2 elements means a combination of tag and data, so on. Okay. So therefore the total size of the cache in blocks can be generically represented as the number of sets multiplied by the associativity. So number of sets multiplied by associativity will give you the total size of the cache in blocks. So if you have, for example, 8 block cache, so the number of sets can be equals to 8 blocks divided by the associativity, which is 2. So that gives you the number of sets as 4. So therefore we have set from 0 to 3, which is the number of sets here. Similarly, in case of 4-way set associative caches, we have the associativity given as 4, the total size of the cache is 8, therefore the number of sets is 2. So if you see this particular block inside the red boundary, you see that it has 2 sets and each set has 4 elements. Okay, that means the number of associativity order is 4, that is there are 4 elements per set, and 4 elements means an element will always mean tag and data. A combination of tag and data constitutes one element. So therefore these are 4 elements in each set. Okay, 4 elements per set. In case of fully associative, that is 8-way set associative, because in this case fully associative would mean 8-way, because the number of sets is 1, and there are 8 elements. So 8 elements would have a combination of tag data, tag data, tag data, tag data, so on till you have 8 elements. Okay, so that's how the structure of each of the different caches, whether we are configuring it as a 2-way set associative or 4-way set associative or fully associative or a direct map cache, would differ from each other slightly in terms of the number of sets and also the number of elements per set. Okay, now let's do one example. Assuming that there are 3 caches, each consisting of 4 one-word block. So there are 3 caches. First is fully associative, second is 2-way set associative, the third one is direct map, and the last one is so we have just 3 basically. Yeah, so it's fully associative, 2-way set associative, and direct. So we are asked to determine the number of misses given by the sequence of block addresses of the RAM as 08068. So the block address is 0. So in that case, in case of direct map caches, the assigned cache block will be block address modulo number of words or blocks in the cache. So it will be 0 modulo 4, which is 0. In case of block address 6, it's 6 modulo 4, which is 2, and then it has the next one is 8, which is 8 modulo 4 is again 0. Okay, so this is the assigned cache block in case of direct map caches. So now if you try to draw the cache structure, this is how it's going to look as. You have the addresses of the block, okay, from the memory accessed, which is 08068, this is sequence, and the hit miss is given here, and the contents of the cache block after reference is given here. Okay, so this is referring to that. So in case of 0, it will be placed in the cache block given by the cache index value 0, which is memory 0, so it's a miss. In case of 8, it's again a miss, and again the assigned cache block is 0. Okay, because 8 is also assigned to 0, so that will be, so memory 0 content will be replaced now with memory 8 content. In case of 0, again next reference, it's again a miss, so memory 8 content will be replaced by memory 0. Then in case of 6, it is assigned to cache block number 2, so that goes here. Okay, the assigned cache block number 2. Then you again have 8, so 8 will replace the contents of 0 in the cache block number 0. So in this case, you see there are no hits being achieved, so all are 5 misses. So therefore, in case of direct map caches with 4 one-word block and a block address of 08068, there are 5 misses that you have. Now let's see what we can do if we would like to improve this. That is, we would like to not have so many misses but to have few more hits. Let's see what we can do. So in this, given a cache block of 4, okay, a cache size of 4 blocks, and the associativity is 2, that is, you have 2 elements per set. Thus the number of sets of set associative cache will be 2. And here let's see what we can do. So we have a block address of 0, so it is 0 mod the number of sets, which is 2, that gives you 0. 6 mod 2, that gives you 0. 8 mod 2, that gives you 0. So this 2 is specifying the number of sets. So it's block address modulo number of sets. Okay, and now again we redraw the cache structure. So you have the memory references given here in the first column, then the hit miss. So in case of 0, it is assigned to set number 0. It has 2 sets and each set has 2 elements. So therefore set 0 and set 0. Okay, we are only referring to the data part. Okay, so it has 2 elements per set. So set 0 is 2 elements, therefore we have set 0 and set 0 twice, and set 1 and set 1 twice. And then again we have 8, so 8 again goes to the cache block, set 0, mem 8. Then you have again the 0th reference. Now this becomes a hit because memory 0 is already there. It was not replaced as in case of direct map caches. Okay, so this, because in case of direct map caches, memory 8 would replace memory 0. But since here we can have 2 elements per set, so here memory 0 is not replaced, and therefore it's a hit in case of the third reference, which is 0. In case of fourth reference, okay, we will replace the content of memory 8 with the content of memory 6 based on the LRU replacement scheme. What LRU states is that I have written here, it is that it actually chooses which entry to replace if you encounter a miss. Now LRU states that the least recently used, okay, block, that is the farthest away in the past, whichever block was used, that will be replaced by the current reference. So least recently used was out of 0 and 8. The least recently used was 8 because 0 was just recently used, and the farthest away that was used was 8. So therefore memory 8th content is replaced by memory 6th content. Okay, and that is here, and in this case this is again a miss. And again then you have the next one, which is 8, so it will be a miss because now again memory 8 will now replace the next one, which is least recently used, which is memory 0. So memory 0 will be replaced by memory 8, so it's again a miss. So as you could see that with this structure, the mapping of two-way set associative cache yields 4 misses and 1 hit, which is certainly better than the direct map caches where you had 5 misses. Okay, so that's how we have improved the average memory access time or performance using two-way set associative cache for this following references of memory. Okay, now let's move to the third case. In the third case, it's a fully associative cache, which is a 4-way set associative cache. In a 4-way set associative cache, there are 4 elements per set, and it is having one set because the total number of blocks is 4. So we just need one set, that is 4 elements per set. So again we have the same references, and we will again go through the hit miss process. So we have the 0th reference that is assigned to, or that is rather searched into block number 0, memory 0, so it's a miss. The second one is 8, it's again a miss because now this goes to the next block of cache, which is here, block number 1. Then you have a 0, so 0 is a hit because 0 is already there, the content of memory 0 is already there, so 0th reference gives a hit. Then you have 6, so 6 goes here in block number 2, and then again you have 8, so 8 is already here in block number 1, so it's a hit. Okay, so since 0 and 8 both are being a hit, so therefore the number of misses reduces to 3 compared to 4 in the last case. So in fully associative caches, as you could see, that the number of misses reduces, and therefore the average memory access time becomes better, that is the performance increases. So therefore with these 3 comparisons, the point I am trying to make here is that the best performance is supposedly possible with the fully associative caches, but the trade-off is that there will be more hardwares that you need because of parallel comparisons needed, okay, using comparator. Now let's look into another example. Assuming that you have a 8 block, okay, cache, and there are and you have a 2-way set associative caches. So determine the hit miss ratio given the sequence of block that is 0, 8, 0, 6, 8. Okay, so it's the same reference, but we are changing it to 8 blocks and see how it makes a difference. The size of the block in the cache is 8, the number of sets into associativity, so the number of sets is 4 because the associativity was 2. Now the mapping process works as follows. You have the RAM address mod the number of sets, so 0 mod 4 gives you 0, 6 mod 4 gives you 2, and 8 mod 4 gives you 0. Now again we go through the same process of hit miss. So the 0th reference is assigned to set 0, okay, So it has 2 elements per set because it's a two-way set associative cache. 8 will again be assigned to set number 0. So therefore it is here M8, then you have 0, so it's a hit now because M0 is already present, the content of M0 is already present. Then you have a 6, so 6 goes on to the set number 2 because 6 is assigned to set number 2, so 6 M6 goes here. Then you have 8, so 8 is a hit because the content of M8 is already available in set number 0. Okay. So therefore what I am trying to say here basically is that when you have increased the number of blocks in the cache, so the cache has reduced to 3 compared to, if probably we recall, it was 4 in the previous example. Okay, now let us have a look at the 4-way set associative cache hardware architecture. Okay, so you have the 32-bit architecture of the RAM right on the top, and then you have the index and the data tag that goes onto the cache structure. So it has a 256 number of entries or sets because it's a 4-way set. So there will be 4 elements per set. So 4 elements per set means here the index that is shown here from 0 to 255 is actually the number of sets. So it's 4 element means we have combination of tag data valid pair 4 times. Okay, because for 4 elements we need this combination repeated for 4 times. So V tag data, V tag data, V tag data, and V tag data. So this is repeated 4 times, and every entry will have or every set will have this 4 elements because it's 4 elements per set. Keep this in mind because it's a 4-way set associative. So the tag from each of these sets, okay, or each of these elements in a set rather, is compared, okay, with the tag of the RAM, and therefore we are doing 4 parallel comparisons using 4 parallel comparators here, and the output is then ANDed with the valid bit. If it is true, then all the outputs of these are fed onto a OR gate. Okay, it's a 4-input OR gate, which means that if any one of it, either this or that or that or that, any one of it is true, then it's a hit because we are making 4 comparisons in parallel, and the output of this is passed through a 422 encoder, which is not shown here in the diagram, but this 4 outputs from these inputs of the OR gate are connected to a 4:2 encoder, and the output of the encoder is connected to the select line of the 4:2 multiplexer, and the input of the multiplexer will be the values coming from the data bit, okay, of each of the elements. So those are the inputs for this 4:2 multiplexer, 4:1 multiplexer, and then depending on the select line of the value that is obtained from 4:2 encoder, the output from this 4:1 multiplexer data is then sent to the processor if it's a hit. Okay, so I'll tell you how we got these values of 8 and 22. Okay, I'll go to the next slide and talk about it. But it's a 4 KB cache that we are basically referring to. So it's a 4-way set associative cache. So it requires 4 comparators and 1 4:1 mux, and the comparators determine which element of the selected set, if any, matches the tag, and the output of the comparator is used to select the data from one of the indexed blocks of the selected set using the mux and the encoded signal. Okay, as I said, it's a 4:2 encoder, so therefore we need a mux and we need a encoded signal for selecting the respective data. The 4-way set associative cache structure has 256 sets, okay, as you could see, from 0 to 255. Therefore the size of the cache in blocks is number of sets into associativity. So 256 times associativity was 4 because it's a 4-way set associative cache. So it gives you 1024 blocks. Okay. Now since each block has one word, therefore the size of the cache in words is 1024 words, which is 1024 times 32 bits is 32,768 bits, which is equivalent to 4096 bytes, which is equivalent to 4 kilobytes, 4 KB. Okay, so it's a 4 KB cache, as I said earlier. So this is the derivation and calculation of how and why it's 4 KB. And from here, the number of bits for the cache index can be given as log 2 of the size of the cache in sets. The size of the cache in sets is 256. Okay, so log 2 of 256 gives you 8 bits. So therefore, we have 8 bits reserved for the cache index. Therefore, the size of the tag bit can be given as 32 minus n plus m plus 2. N is 8, m is 0 because it's just having one word per block, and 2 is for byte offset. Therefore, the size of the tag bit is 22 bits. So now if you go back to the diagram, you will see that therefore we have 22 bits reserved for the tag and 8 bits reserved for the cache index. So that's how this number 22 and 8 has been generated. Okay, now let us move to the next part of this. Let us try to find out a trade-off between the size of the tag versus set associativity. Okay, how is the two related to each other? Now, increasing the associativity requires more comparators, as you have seen, and therefore it requires more tag bits per cache block because we are doing more comparisons. So keeping this in mind, let's do one example. Okay, assuming that a cache of 4K blocks and 4-word block size and 32-bit address, find the total number of sets and the total number of tag bits for the following caches. So you have a direct map cache, you have a 2-way cache, a 4-way cache, and a fully associative cache. Now in case of direct map caches, since it's a 4-word block, so 2 to the power m words per block, which is 2 to the power 2 words per block, which is 2 to the power of 2 plus 2 bytes per block. Therefore, the tag size can be given as 32 minus n plus 2 because m is 2 and 2 is for byte offset. So therefore the number of tag bits and the index bit is equivalent to 28 bits. Okay. Now since you have 4K blocks, therefore log 2 of 4K gives you 12 bits. So therefore the cache index size is n equals to 12 bits reserved for cache index. Therefore the number of tag bits can be given as 28 minus 12, which is 16 bits. Okay. Now this is the number of tag bits reserved for each block. Okay, each block, or each, rather you can say each entry. Okay, because every block will have a tag, that is every entry will have a tag. Okay, so every entry has a tag bit of 16 bits. Therefore the total number of tag bits will be 16 bits into the total number of entries or total number of blocks, which is 4K. Okay, this is 4K given. So therefore 16 bits into 4K gives you the total number of tag bits as 64K tag bits. This is the total number of tag bits in the entire cache structure, not just for one entry. Okay, now let's move to the next one. So we know that each degree of associativity decreases the number of sets by a factor of 2 and thus decreases the number of bits used for index by 1 bit. Okay, the number of sets decreases by a factor of 2. This is obvious because when you have the degree of associativity increase from 2 to 4, then obviously the number of sets will keep decreasing by a factor of 2. Okay, because it's always a power of 2 in which the size of the cache is specified by. And since the number of bits used by the index is decreasing by 1 bit, therefore the number of bits used for the tag bit increases by 1 bit. Okay, because we have to stick to the 32-bit number. Okay, so keeping this in mind, let's do the next part of it. So for a 2-way set associative cache, the total size of the cache in blocks equals to number of sets into associativity. The total size was 4K, number of sets into 2, so therefore the number of sets is 2K. Okay, therefore decreasing the number of index bits by 1 bit means that in the previous case the number of index bit used was 12. So if you reduce it by 1 bit, it gives you 11 bits. Therefore the total number of tag bits for 2K set is 28 minus 11, that is a tag bit size for each data. Okay, and that will be multiplied by 2 because it's a 2-way set associative cache, that is 2 elements will be there per set. So therefore it is multiplied by 2, right? And then that is multiplied by the number of entries. Okay, the number of entries means the number of sets that are available. So that is 2K. So therefore 28 minus 11 multiplied by 2. So this multiplied by 2 is actually giving you for the total number of sets, which are 2, how many tag bits are reserved, and that is multiplied by the total number of sets that is available. Okay, so two elements, each element having 28 minus 11 number of tag bits. For two elements, that is into 2, and for the total number of sets is into 2k. So that gives you 68 kilobits. For the third case, for fully associative, the index bit is 0 because you just have one set, okay, with 4k blocks. Therefore the tag bit is 32 minus n plus m plus 2, so n is 0, m is 2 because we have forward per block, as you have seen in specified in the question itself. This is forward block, so m is 2, and 2 for byte offset, so therefore the number of tag bits is 28. Now since we have 28 tag bits and there are total number of 4k elements present in the only set available, which is only the single set available, there are 4k elements, so this therefore becomes 28 bits into 4k, and the number of set is 1, so into 1, so that gives you 112 kilobits, okay, for the total size of the tag for fully associative caches. Okay, now let's move to another type of example where we will try to see why multi-level caches are better in performance than single level caches, okay, or no caches at all. So as we know, the average memory access time is equals to hit time, that is the latency, plus the miss rate times the average miss penalty, which is AMP. So the values are given here. The metrics are hit time for L1 cache it's 2 cycles, for L2 cache it's 10 cycles, and for no cache it's 100 cycles, and for multi-level cache it's 2 cycles for L1 and 10 cycles for L2. And the hit rate is 90% for L1 cache only, for L2 cache only it's 97.5%, and for no caches it's 100%, okay, because everything is present in the RAM. And for multi-level caches it's 90% for L1 and 75% for L2. So now let's see how to calculate this average memory access time. So EMAT for L1 cache is equals to the hit time for L1 cache plus miss rate of L1 cache times the average miss penalty of L1 cache. So the hit time for L1 cache is given as 2 cycles, okay, we have these 2 cycles given here, plus the miss rate is given as 10% because the hit rate is 90%, so miss rate will be 10% multiplied with the average miss penalty. Average miss penalty means if the cache doesn't hit, then the miss penalty will be 100 cc because it will have to look into the RAM. So this is 100 cc here, so that gives you a value of 12 cc. And EMAT for L2 cache will be hit time for L2 cache only plus the value of the next one, which is given as sorry. Okay, so we are back. So what I was talking about basically is let me just check it's so what I'm trying to basically say is for average memory access time for L2 cache will be the hit time for L2 cache plus the miss rate. So miss rate is 2.5% because the hit rate is 97.5%, and the average miss penalty will again be 100 cc because if it is not there in L2 cache, then it has to look for the value in the RAM, so which is 100 cc in case of no cache. So that gives you a value of 12.5 cc, because the hit time was 10 cc. Okay, and the value for multi-level caches will be the hit time for multi-level cache for L1 is 2 cc, which is given here, plus the miss rate into AMP will be, miss rate is 10% because 90% is the hit rate for L1, so the miss rate is 10%. So miss rate is 10% times the average miss penalty will again be the time that you look for it in the L2 cache. So it is 10 cc, okay, for L2 cache, plus the miss rate for L2 cache, which is 75% was hit rate.